You're welcome to today's tutorial video on nodal analysis. So basically, nodal analysis is all about analyzing circuits with node voltages as the circuit's variables. And we do nodal analysis because it helps us to reduce the number of equations that we must solve simultaneously to be able to analyze the circuit. And for nodal analysis, what you need basically is Ohm's law, then also Kirchhoff current law, KCL. Now for Ohm's law, there's just one particular rule that you need to get, and that is current flows from a higher potential to a lower potential. That's basically all you need to know about Ohm's law, because you are going to apply it in solving the questions on nodal analysis. So when you have a circuit and you are being asked to analyze it with nodal analysis, the first thing you have to do is to find the number of nodes. So we all know that a node is a point of connection in a circuit where currents meet or they split. Then also it's a connection of two or more branches. So first you find the number of nodes, then you select a node as a reference node. After doing that, you assign voltages to the remaining n-1 nodes. Then you apply KCL to each of the n-1 non-reference nodes. Then you use Ohm's law to express the branch currents in terms of node voltages. Then the rest is simultaneous equation. You obtain your node voltages. Now for nodal analysis, we have two cases. Nodal analysis with voltage sources. So the first one is if a voltage source is connected between a reference node and a non-reference node. And then the second one is if the voltage source is connected between two non-reference nodes. But for this tutorial, we are going to look at just the first case, if a voltage source is connected between a reference node and a non-reference node. Okay, so I'm going to use this circuit as an example to explain the steps that I gave earlier. So we said that we have to select a reference node, and usually the reference node is called the common ground. So we are going to use our ground potential as our reference node, and it's at a zero potential. That's why you see the zero here. Then we have two non-reference nodes. The nodes which are not reference nodes are non-reference nodes. So we have the two non-reference nodes here. Now these non-reference nodes are going to determine the number of equations that we are going to solve simultaneously to be able to get our node voltages. So since we have two non-reference nodes, we are going to have two simultaneous equations to get our node voltages V1 and V2. So after this, we have to assign currents to the nodes. And for this example, you see that I've assigned current I1, current I2, and current I3. One thing you should note is that once you assign the current in a certain direction, or for a resistor, you don't assign another current at the other end of the resistor. It's the same current. So we have I2 here, I2 here. It's the same I2 that is going through resistor R2. So at node 2, we can see current I2, I3, and then the capital I2 also coming to the node. So we are going to write the KCL equations, then express them in terms of voltages to be able to get our two equations to find the node voltages. So at node 1, KCL states that the sum of currents entering a node should be equal to the sum of currents leaving the node. So at this particular node 1, capital I1 current is entering the node. So we have I1, and that is the only current entering the node, equals I2, capital I2 is leaving the node. Then small I2 is also leaving, then I1 is also leaving the node. So we have I1 equals I2 plus I1 plus I2. So expressing it in terms of voltage, I1 is a current source, so we are going to leave it as that, I1. Then I2 is also a current source, so we are going to leave it as that. Then the other currents as a result of the voltage drops, we are going to express them in terms of voltages. So we have I1 to be V1 minus 0 over R1. At the beginning, I told you that the most important thing you need to know about Ohm's law is current flows from a higher potential to a lower potential. So depending on the direction of your current, that is going to show which part is your higher potential and which part is your lower potential. So I have my current I1 coming downwards to tell you that the point at V1 is my high potential. Then the reference node, which is 0, is my low potential. So from higher potential to a lower potential. So I have V1 minus 0 over R1. Then for I2 is entering the node V2. So from a higher potential to a lower potential, that means that I'm going to have V1 minus V2 over R2. This is a current expressed in terms of voltage. This is also a current expressed in terms of voltage. Then at node 2, I have my I2. Then I3 to from a higher potential to a lower potential. So that gives me V2 minus 0 over R3, basically. So this is to give me two equations to solve simultaneously to get V1 and V2. And that's basically it. So let's look at circuits with real values, real numbers, and see how best we can solve it. Okay, so let's take our first example. For this circuit, we would select our reference node. So a ground here, making our reference node here. Then we have two non-reference nodes. So this first part is our first reference node, non-reference node, sorry, V1. Then we have V2 here. So the next thing we will do is to assign current directions. Yes, so say we have here to be I1. And one thing you have to know is that you can assign current in any direction that you want. So as I've assigned mine going down, yours can go up, but you have to make sure to follow the principle of current flowing from a higher potential to a lower potential when you are writing your voltage equations. So I1 here, then I assign this to be I2, then here say I3, then I'll call this 10 amps I4 and this 5 amps I5. Assign it in the same direction. You can choose an opposite direction. That means that it's going to be negative, but whatever you do, you have to follow the rule. Current flows from a higher potential to a lower potential, so choose which potential you desire as your higher potential. Okay, so we are going to now apply the KCL, write the KCL equations and express it as node voltages. So for node 1, that's V1. At the node, we have current I5 entering the node. Then I1 and I2 are leaving. So I5 equals I1 plus I2. As we said, current entering the node, sum of the currents entering the node should be equal to the sum of the currents leaving the node. So I5 is entering, I1, I2 are leaving. So current I5 is 5 amps. Write our 5 amps. Then I1, considering the direction that I have taken, it means that V1 is my high potential and the reference node is my low potential. So it's going to be V1 minus 0 over this resistance, 2 ohms. Then for I2, V1 still my high potential, then V2 my low potential, so V1 minus V2 over 4. So I'm going to simplify this equation, multiplying through by 4. I have 5 times 4 to be 20. Then 4 multiplying this will give me 2V1. Then here I have V1 minus V2. Simplifying further, I have 3V1 minus v2 to be equal to 20, and that is my first equation. Then at node 2, I have current I4, which is 10 amps, entering the node, current I5 leaving the node, then current I3 leaving the node, but I2 is entering the node. So here I have I2 to be equal to I3, okay, but I4 is also entering the node, so I4 plus I2 entering the node, I3 leaving, then I5 also leaving. So that makes our equation set. Then I4 we know is 10 amps, so we write out 10. I2 V1 minus V2 over 4. Then I3, 0 is my low potential looking at the current direction, so it's going to be V2 minus 0 over 6 plus I5, which is 5 amps. Simplifying this, I'm going to multiply through by 12, so this gives me 120 plus 3v1 minus 3v2 equal to 2v2 plus 60. Then simplifying this further, I'm going to have 3v1, then I have 3v2 here, 2v2 at the other side. When I cross over, it becomes negative, so it gives me 5v2 equals to, then I have 60 here, moving 120 over, I'm going to get minus 60, and that gives me my second equation. So solving these two equations simultaneously, so using my calculator to solve the two equations simultaneously, I have 3 minus 1, 20, then 3 minus 5 and minus 60. So that gives me my V1 to be 13.33 volts and my V2 to be 20 volts. As simple as that. So for our second example, we have this circuit. Here we have our ground, which is going to be our reference node, and it's at a 0 potential. Then we have 3 non-reference nodes. Here V1, then V2 at this point, and then V3 here. And for this circuit, we are to find the value of Ix. So we need to find our node voltages to be able to find the current Ix. So we are going to assign current directions as usual. We have 3 amps here. I'll call this 3 amps I1. Then assign a current here coming inside, which is I2. Then say, okay, this is already Ix. Then assign a current here I3. Then 1 here I4. Still take note, you can assign any current direction that you want. So at node 1, I have current I1 entering the node, Ix leaving, and I2 entering. So I have I1 plus I2 to be equal to Ix. Then I1 we know is 3 amps. Then I2, so considering the current direction that I have taken, V3 will be my high potential. So V3 minus V1 over 4 gives me current I2. Then I have Ix to be V1 minus V2 over 2. So I'll simplify this, multiplying through by 4. Then I have 12 plus V3 minus V1 equals to 2V1 minus 2V2. Simplifying further and rearranging the like terms, I'm going to have minus V1, 3V1. Then positive 2v2 then plus v3 being equal to minus 12. If I multiply through by negative 1, I'm going to get 3v1 minus 2v2 minus v3 to be equal to 12 as my first equation. So for node 2, current I3 is leaving the node, Ix is entering, and I4 is leaving. So I have Ix to be equal to I3 plus I4. So Ix we know is v1 minus v2 over 2. I3 is v2 minus 0 over 4. Then I4 is v2 minus v3 over 8. So multiplying through by 8, I get 4v1 minus 4v2, giving us 2v2 plus v2 minus v3. Simplifying and arranging the terms, I'm going to get 4v1, then I have this 2 coming over, minus 6v2, this one, so minus 7v2 plus v3 to be equal to 0, and this is my second equation. Since we have 3 nodes, we are going to have 3 equations that we will solve simultaneously. So we will analyze node 3. Node 3 has a current dependent current source, so we would need Ix here, which we already know. We would need to substitute it in to make our equation complete. So at node 3, we see 2Ix leaving the node, I4 entering, and then I2 also leaving. So I4 will be equal to 2Ix then plus I2. But I4 is v2 minus v3 over 8. 2Ix, we already know Ix to be v1 minus v2 over 2. So we'll substitute that in. Then I2 is v3 minus v1 over 4. This 2 cancels this 2. Then we multiply through by 8, and we have v2 minus v3 giving us 8v1 minus 8v2, then plus 2v3 minus 2v1, giving us 0. So we have v1 to be 4.8 volts, v2 to be 2.4 volts, then v3 to be minus 2.4 volts. And as I said earlier, we are to find the current Ix. So from our equations, we know that Ix is v1 minus v2 over 2. Ix to be 4.8 minus 2.4 over 2, and that leaves us with Ix being 1.2 amps. So in the beginning of the tutorial, I said that for nodal analysis with voltage sources, we have 2 cases. We have solved questions on circuits that didn't have any voltage source. So we are coming to look at a circuit with voltage sources. Now, I said early on that we have 2 cases, but we are going to look at just one for this tutorial. And the first case is when you have your voltage source or sources between a reference node and a non-reference node. So for this circuit, we have our reference node here. Then we have nodes V1, V2, and V3. So we can see that V1 has a voltage source in between it and the reference node. V3 too has a voltage source between it and a reference node. So for the first case, all you need to do is that if you have a voltage source between a reference node and a non-reference node, you assign the value of the voltage source to the non-reference node. In other words, V1 becomes 40 volts and V3 becomes minus 20 volts. Basically, as simple as that. So we are going to analyze the circuit. We have node 2. Since we already know what V1 and V3 are, we just need to write the node equation for node 2. But before then, let's assign our current directions. So let's say we have current I1 here. Then we'll call this 5 amps current I2. We'll call this I3. Then this I4. Basically. So at node 2, current I1 is entering, current I3 is leaving, I4 is leaving, and I2 is entering. So we have I1 plus I2 giving us I4 plus I3. I1, as we can see, is V1 minus V2 over 2. Then we have I2 to be 5 amps, I4 to be V2 minus V3 over 8, then I3 to be V2 minus 0 over 4. But we already stated that V1 is 40 volts and V3 is minus 20 volts. So we are going to substitute this into our equation. Then we have 40 minus V2 over 2 plus 5 giving us V2 minus 20, which gives us positive 20 over 8 plus V2 over 4. So simplifying this expression by multiplying through by 8, we have here to be 160 minus 4V2 plus 40 to be equal to V2 plus 20 plus 2V2. Rearranging them, I have minus 4V2 minus V2 minus 2V2 being equal to 20 minus 160 minus 40. This gives me minus 4 minus 2, that is minus 6 here, minus 7V2 to be equal to 20 minus 160 giving us minus 140 minus 40, which is minus 180. So V2 gives us minus 180 over minus 7. So we have minus 180 over minus 7. And that gives us V2 to be equal to 25.7 volts. So that is how you solve nodal analysis questions when you have voltage sources between a reference node